what this homework was all about was our acids and bases, so really kind of understanding what's happening within those. So if we were to go through some kind of simple stuff first, let's look at a generic acid-base reaction. So what would be a generic characteristic of an acid? Okay. So if we looked at it to begin a reaction, we'd have a hydrogen, and that hydrogen would be connected to something. Okay, we could use the letter A to represent our acid, and in the course of this chemical reaction, that hydrogen goes somewhere else. I'm actually going to modify this a little bit. So that hydrogen would split off away from the A. How would we expect the electrons in that bond between HA to move? So apart, they go with the hydrogen?
No, they go with A.
Okay. We would expect the electrons to go with the hydrogen because our definition of an acid is an H plus donor, which means that H plus has to come from our acid. A has to take the electrons away. If we take electrons away from the hydrogen, it would become positive, so there's our H plus. A, having now taken those electrons back, would have gained a lone pair of electrons and would then become negatively charged. Okay? So this is just looking at HA acting as an acid. Okay? Chemical reaction, we need to react that with something. Okay? What do you think we'd react with an acid? A base. So a good symbol for a base could be B. What characteristic does the base need to have? It has to accept hydrogens. So if we look to the product of this, there has to be some kind of modification happening there where that hydrogen is now connected to the base, right? So if we go back to the reactant side, what did the base have to make that bond to the hydrogen? It had to have electrons because that hydrogen is coming off as H+. It has no electrons to make the bond. So what did the base, the B atom, need to supply? Electrons. How could we show that? A lone pair of electrons. So if we were now going to push a mechanism, we could say the base donates its electrons to our hydrogen. The electrons move away from our hydrogen to A, and we've now done an acid-base reaction. That's it. Right? That's your kind of fundamental process behind this. Okay? Things that we could look for to predict whether this reaction was likely or not have to do with the stability of the reactants versus the products. This is a generic form, so it's really hard to establish what was more or less stable than anything else. Okay? But typically where we would look would be for the charged things. The more charged something is, the more unstable it is, the more reactive it is. Okay? So HA theoretically is neutral, so is B, but what is B supplying? The electrons. So this is probably more often than not negative. Okay? And if we look at this product of those reactions, that A, once it's lost its hydrogen, is also negative. What we can now do is compare those negatives to each other. We could just as equally compare HA to HB. The problem with comparing HA to HB is that all of the chemistry is hidden in bonds. Right? So we don't see anything obviously reactive. B negative and A negative are obviously reactive because we can see the negative charge. Right? So if we're thinking through trying to decide where this reaction goes, what we would now compare is B negative to A negative. Whichever one was more stable is the direction the reaction goes. Okay? So if B with the electrons was more stable than A with the electrons, I would predict the reaction to heavily favor the reactants. Because reactions don't go to make things unstable, they go to make things stable. So if B was more stable than A, I would expect no reaction. I mix B with HA, nothing happens. That's what that would mean. Right? What determines my reactivity? It's tied to the amount of electrons. Electronegativity is a contributing factor as well. Okay? Charge, size, electronegativity, resonance, induction, and then hope and pray we don't have to deal with it in this class. Okay? Those rule sets are helping you to focus on the bigger, more important things. Okay? Two people are running at you. Which one are you more concerned about? The larger one. The other one's smaller, but it's holding a gun. Really? You care about the big one? Your focus shifts, and it changes depending on those different systems. But we start with kind of these big picture reflexes. Oh, bigger, that's more dangerous. You probably wouldn't even see the gun until it got closer to be like, oh, that's a problem. Okay? So when we talk about those relationships, that's why we start looking at charge. Then we move to the size of the atoms. Then we move to electronegativity. Then we move to resonance. Then we move to induction. And then we've got a whole crap ton of other small things that can change out how the reactivity balances out. Okay, so what you have to think through is how each of those categories affects the overall stability of what you're looking at. This is one of the reasons why we pick the things that are negative or the things that are charged. Because if they're charged, they already stand out as potentially reactive. That's the very first thing we look for, is charge. So if I compared A to B, okay, those are both the source of electrons. And whoops, what I'm trying to decide is what happens in this box. Should the reaction progress forwards or not? Okay, so as it's drawn, what do you think? It may be more helpful. Well, actually, no, I think that's fine. Do we think this reaction as drawn should progress forwards? Should we produce products? Why? So what are you using to make your comparison? Charge, size, electronegativity, resonance, or induction? Okay, the charge. What are you comparing in the charge?
The reactant side doesn't have a charge, and the product side does.
Okay, I'll accept that. We should be able to refine that a little bit further and say the B, the thing that's supplying electrons, versus the A at the end. Okay, so cool, you are identifying the critical difference, but now the question is, are you interpreting that difference correctly? When we run a reaction, do we want to form more neutral things or more charged things? Neutral. Everything's striving for neutrality. We're trying to get to lower energy states. Charged is higher in energy. So if we look at this and we compare B to A minus, which one is more charged? A. So where should the reaction go? Towards A or away from A? This reaction should heavily favor the reactants. So you followed the right logical thought process, but then you swapped the logic at the very end. Okay? So that's a simple fix. You just have to make that adjustment. So this is one of the reasons why we talk through about the stability of individual species and why we look at where electrons are located within molecules all the way through the rest of the semester, so that we can get to this point and now say, what's the difference between those? What is good, what is bad? Okay? We've slowly been building. This isn't new. This is, we're adding a base layer so that now we can actually do something interesting and useful. Okay? So if we have any weaknesses in that base layer, what happens? Yeah, the whole system crumbles. Okay? This is why we try to spend some time very carefully evaluating our structures, very carefully evaluating where charges are, very carefully building that base layer so that when we advanced, we had a solid foundation. Okay? What's going to happen in the next unit? We're going to get even more advanced, and it's going to require everything underneath it. So if there's a weakness at any point through that system, it's going to get capitalized on with every single question. This is why we spent so much time, believe it or not, looking at Lewis structure, looking at the stability of structures, looking at how reactions work so that we can understand those fundamentals that we can now build outwards. Okay? And if we have weaknesses in those fundamentals, that doesn't destroy building outwards, but it's going to change what you do building outwards. Building outwards is not going to be, let's apply and understand what's going on. It's going to be hoping like crazy that you can memorize the raw facts of each of those reactions. Okay? Realize that as we try to memorize those raw facts, the structures are going to change, which makes it look like the facts are changing, and they aren't. Okay? That's why I wanted to spend a lot of time understanding structure and our fundamental rules so that we could build upwards. But I fully appreciate that it is very hard to trust a new instructor. Unfortunately, sometimes we have the best things in mind for you. Sometimes we don't. Okay? So if we now look at this structure, draw the conjugate base for the following acid. Okay? So we got a bunch of words here and we've got a structure. We don't have any reactions, we don't have any other information, so you have to be able to interpret what these words mean. What is an acid?
Donates hydrogen.
Does it donate H radical, H with a lone pair, or H with no electrons?
No electrons.
Okay? So we have to be very careful in knowing exactly what's happening within that. We're talking about donating H+. Okay? And if we go through and look at that starting structure, okay, if we look at it as an acid, our HA, I shouldn't have erased everything, donates the H+, generates A-. What does it donate the H+ to? To a base. Okay? So draw the structure of the conjugate base for the following acid. This is the acid. That's its conjugate base. How do I know the A- is a conjugate base? Well, what's the definition of a base?
Accepts H+.
And what needs to happen for A- to become HA? What do I need to change to the structure to make A- look like HA? So let's try it this way. Here's an A. I want to make it look like HA. What do I have to do?
Attach an H or an electron.
You mean it has to accept a hydrogen?
Yeah.
Yeah. So what does that mean? A- is the conjugate base for our HA acid. Okay? So for this question, draw the conjugate base for this acid. We're saying that is HA. You need to remove a hydrogen. Okay? The question gets a little bit vague here because there's some implied content behind it. Not all hydrogens are created equal. And you should be removing the correct hydrogen. You should be removing the most acidic hydrogen. Okay? Which hydrogen do you think we're talking about?
The one attached to the oxygen.
Why not this hydrogen? Or this hydrogen? Or this hydrogen? Why do you think it has to be the hydrogen out here?
Like you said, it doesn't have to do with acidity.
It has to do with acidity. Awesome. Oh, I like that. Okay. So why are you saying that blue hydrogen is the most acidic? You just know. Okay.
Oxygen has a higher acidity, or lowest hydrogen.
So we can't really say oxygen has a higher acidity.
Or is
We
it
can
less
say the
than-
hydrogen connected to an oxygen has a higher acidity. Okay. Why?
That has to do with electronegativity.
Okay. So we just talked through, we said there's rules. Charge, size, electronegativity, resonance, all of those things contribute to our overall acidity for an individual molecule. And if we're going through and looking at the ability to donate H+, what's going to change that? Well, if we look at the red one, what would happen to the carbon if we donated H+? What would happen to that carbon? If I got rid of that H+,
It become negative.
becomes negatively charged. What happens if I get rid of the blue hydrogen? What happens to the oxygen?
It gets a
Also
low
charge.
charge.
Okay, so that's interesting. The exact same thing happens as is the red one, and yet we got different answers. Okay, it becomes negatively charged. That's it. How does it become negatively charged? It's gaining a lone pair. Okay, the problem was just saying gaining a lone pair, since we didn't specify any lone pairs, and if we now just draw one, does that one of the ones it was supposed to have, or is that an extra one? How would I know? I wouldn't. Okay, so this is why you'll typically see people drop lone pairs, because when we add that lone pair on, we don't know, is that an extra lone pair, or is that supposed to be there, or is it now missing an octet? All of those things back in Lewis structure now start to come snowballing back. Okay, when we look at the carbon structure, our red structure, we could just add a lone pair to represent it, because that's all that would happen. It didn't have lone pairs already, because we knew the Lewis structure for our carbon out there. Okay. And if we now look at those two structures, blue versus red, is one of them better than the other? Oh, okay.
Blue.
Okay. So that's awesome. She's volunteered. The blue looks better. But now you can't explain because you volunteered that. The rest of the class must explain why the blue looks better.
The oxygen electron negatively keep the electron better than carbon.
Oxygen is more electronegative than the carbon. Because oxygen is more electronegative, it can hold the electrons better than the carbon. So what's your explanation? An electronegativity difference. Oxygen is more electronegative than carbon. That's why it's able to stabilize that negative charge better. Which means if I want to draw the structure of the conjugate base for the following acid, drawing the red structure, full disclosure, would immediately get me going wrong. Okay? You could theoretically come back and challenge and say, well, you didn't tell me to draw the best conjugate base, which is really just a cop-out, and you're hoping and praying that a little bit of knowledge allows you to now say that you're good. Because if you knew that to begin with, would you have drawn the red one? No, you should have drawn the blue one. Okay? There's our conjugate base. How do I know that's a base? What does the base need to do? Accept hydrogens. Where would it accept hydrogens? Yeah. On that negatively charged atom, that would be a great place to put a positively charged hydrogen. Yep, that would be exactly why that's the conjugate base. Does that make sense? So we very heavily lean into those definitions because those definitions are what allow us to build and apply outwards. Questions about that one? 3, 2, 1, delete. Okay. The following illustration shows the molecule aspartic acid, fully protonated. What is aspartic acid? Anybody know? You can be like, no, that's fine. That's your next semester. That's biochemistry. So if you have to take biochemistry, you'll be responsible for understanding aspartic acid and what it looks like in the body. Because it doesn't look like that in the body. Okay? Its hydrogens change locations when we move into the body, because in the body, we don't want to be strongly acidic. We don't want to be strongly basic. We want to be as neutral as possible. Okay? Neutral does not mean all of our structures have no charge. Neutral means we've established a baseline where our structures are unreactive at that pH. Okay? That requires some pretty heavy acid-base chemistry, which is a bit unfortunate because all of that acid-base chemistry shows up where? Second semester general chemistry. And how many of you needed to take second semester general chemistry? None of you. Which means when you move to biochem, you get this very rude awakening of, well, what the hell? Why am I missing all this content? You're missing all this content because somebody didn't think it was important and that you could just memorize your way out of it. Which means you're setting yourself up to now memorize a whole hell of a lot of stuff. Okay? You either apply or you memorize. Those are your two choices. Okay? Biochemistry gets a little bit easier to memorize because it's not an infinite amount of molecules that we can study. It's now a very narrow field of molecules. It would be 20 amino acids. Okay? It would be the carbohydrates. It would be glucose. Okay? So it narrows the field of chemical molecules, so you don't have to know everything. You just have to memorize what can happen on a single molecule. That makes life a lot easier, so generally people see biochem as easier than OChem. Okay? pKa values, okay, are all of those. Oh, we didn't talk about pKa's. This isn't one that's fair. I wouldn't ask this one on a test. But what I would do is modify it a little bit. Biochem would push you on this one, for the record. We have acidic, and basic conditions. Okay, what is neutral pH?
7.
7. So if we have a value lower than 7, that means we are acidic. If we're higher than 7, we're basic. Okay? So if we look at our structure, okay, they're talking about the acidic hydrogens. So where are the acidic hydrogens in this molecule?
The OHs.
Cool. And officially, it's not the OHs, it's the H on the OHs. Okay, so a subtle change to that. I want to color code that slightly differently so we can see that. Are there any other acidic hydrogens? For reference, how many did they give you? They give you 3 values, which means there's 3 things that were potentially acidic.
Hydrogen on the nitrogen.
The hydrogen on the nitrogen is also acidic. Okay. Why is the hydrogen connected to the carbon here not acidic?
Because of its bond.
What about its bond?
Non-polar.
Why does that make it not acidic? It's actually not a bad explanation. It's not the explanation I wanted. It's not a bad explanation.
Because of the covalent bond forces.
It's not as electronegative as
Okay, so we could bring electronegativity into it. We'll come back to yours because I like that explanation as well. Okay. What is electronegativity in reference to?
It's wanting to steal electrons.
Steal electrons. If oxygen is more electronegative than hydrogen, what is it doing to the electrons in that bond? It's taking them away, which means what happened to the hydrogen?
It has no electrons.
True.
added onto the oxygen.
If it has no electrons, what happened to the hydrogen?
It's a proton.
It's positive. What was the definition of an acid?
Positive hydrogen.
A positive hydrogen. There's your acidic hydrogen. Okay. Why does that not happen with that green hydrogen?
Because carbon doesn't steal its.
Why does carbon not steal the electrons from the hydrogen?
Because it's not.
You can run a couple different runs on that.
Polar.
Okay, we could say by definition it's a nonpolar bond, Mike. Therefore, the carbon can't steal the electron. Well, why is it a nonpolar bond? What dictates polar versus nonpolar versus even ionic?
The relationship between the two atoms.
True. What is that relationship? It's not forces, because the forces are what's dictating those out. What dictates what type of bond we have?
If it's like a metal or a non-metal, is that what you're?
Cool. That was our approximation that allowed us to cheat and not memorize the hardcore definition. What was the hardcore definition?
Organic.
Electronegativity.
Oh.
The electronegativity is the ability to steal electrons from another atom. If we bond carbon next to hydrogen, what are their electronegativities? Almost identical, which means does one get to steal from the other? No, they're pulling with the same strength. There's no stealing. But if we look at oxygen versus hydrogen, their electronegativities are very different. That's why oxygen can steal the electrons. So if we're looking for acidic spots, what we're looking for is hydrogens connected to very different elements. And in particular, there are electronegativity ones or electronegative ones. Right? So if we now go through and look at this, if we're at a pH of 1, what does that mean? We are super acidic. And if we're super acidic, are we going to be able to remove the hydrogen from the basic atom? No. It's basic. It wants to hold hydrogens. And if we're super acidic, we're saying, keep it, keep it. What about from an acidic one? Well, it's acidic. That depends. Where's the line? We're at a pH of 1. Are we more acidic than the value? Yeah. Are we more acidic than the value? Yeah. 2 versus 1. We're still lower on that pH scale, which means what?
More acidic.
This solution, or that molecule, keeps all the hydrogens. Which means what's the structure? Yeah, nothing changes. Okay? It keeps all those hydrogens. Biochem will push on that a lot and say, well, what happens at pH 2.5? What happens at pH of 4? Okay? And you can understand all the mathematics behind it, or you cheat your way out of it and you just memorize what happens at each of those changes around those numbers. How do you do that? For an infinite amount of things? You don't, which is why it's not recommended for organic chemistry or even for general chemistry. Where is it recommended for? Biochem, because it's not an infinite amount of things. How many things is it? It's a bit rough there. At its extreme, it's 20. Why 20?
For the 20 essential amino acids.
There's 20 amino acids. Right? So you don't have to memorize a million different things. You just have to memorize it for those particular ones. And even then, you only have to memorize it for the ones that can gain or accept hydrogens. Right? So for instance, we excluded this one. Right? Why could we exclude that one? How is that one?
Gain or donate.
Why does it not gain or donate?
Because of its electronegativity. It doesn't steal the electrons.
Close.
from
It's
the
not.
hydrogen.
There we go. So it's a comparative. The electronegativity difference between those atoms is negligible. Whereas the electronegativity difference between nitrogen and hydrogen, that's huge. Oxygen and hydrogen, that's huge. So when we say we have to memorize it for 20 amino acids, that's false. How much do you guys know about amino acids? Are all amino acids, do they all have nitrogen and oxygen? Depending on how you want to answer that question. But the answer we're going for is no. They don't all have oxygens and nitrogens, so we only really need to worry about the ones that have oxygens and nitrogens. That's it. That greatly reduces the amount of memorization you have to go through to do to answer questions like this on how it modifies the structure. Kind of make sense? So when we start talking about our chemical reactions, we want to use curved arrows to explain how the electrons move. If the electron's moving changes the bond connectivity. So one option that we could go through and do would be just look at the overall reaction to begin with and be like, how should the electrons move? Where do you think an arrow is going to start on the reactant side? Took too long. What do arrows show the motion of?
Transfer of electrons.
Okay, the movement of electrons. We've got to be a little bit careful, and I think I've used transfer in the past too. We've got to be careful with that because transfer can be oxidation and reduction, and that's not what's happening here. Transfer is sharing of electrons or unsharing of electrons. Okay, so we're moving electrons. So what should we look for first and foremost? Okay. If our mechanism is all about moving of electrons, should we look to hydrogen? How many electrons does hydrogen typically have? Think about our acids. Define an acid.
Just one.
Define an acid.
Donates.
Does it donate just hydrogen?
H
H what?
plus.
Plus, which means hydrogen in a lot of cases has how many electrons?
0.
0. So looking for hydrogens to move electrons is probably not your best source. Where should you look for electrons? So the biggest screaming thing would be look for the negative thing, because the negative thing is going to have a lot of electrons. Okay? It doesn't have to be the negative thing. It could be anything with lone pair electrons. Oxygen would be a great example of that. So if we go through and look at this, where do we have electrons? On the oxygen and the sulfur. Why should we look at the oxygen electrons, not the sulfur electrons? The oxygen is negatively charged. It has more electrons than it can handle, which is why it's negatively charged. Okay? So it wants to neutralize that charge. So it needs to share those electrons with what? Be more generic. I like that. You're absolutely right. It should share with the hydrogen. But why the hydrogen? How do I neutralize a negative? I loved adding, and then you said protons. Protons, again, isn't necessarily bad. Just adding positives. That's all you need. How do you get rid of a negative? Put a positive next to it. Ta-da, done. It's gone. Okay? So we could now look at the other structure and say, well, what thing is the most positive? Okay? And you said hydrogen. Why is the hydrogen positive? Okay? I'm going to cheat because we're talking about acids and bases, Mike. So hydrogens are acids. They're positive. Fair. Not good enough. Do better. Why? There you go. So if we know our electronegativity differences, we know that sulfur is taking electrons away from the hydrogen because the sulfur is more electronegative than the hydrogen. That's polarizing the bond, causing... Whoa. You all got lucky. You almost got a pen thrown at you. Okay? Causing the electrons to go to the sulfur. Okay? And now that I look completely at the question, I've got to ask a follow-up. Why did you say the sulfur was more electronegative? Awesome. That's exactly what I wanted to hear. Fantastic. I didn't want you to hear you say it because I looked at the product. Okay? Which would have been a fair answer. Okay? But if you know your trends in electronegativity, you mean the things that you were told to pay attention to early on in the semester? Yes, exactly those. Because we apply and use those to build and predict our reactions. That's why we need that information. Okay? So if we're now looking at this, what happens? The oxygen shares a pair of electrons with the hydrogen. If we share electrons with hydrogen, what have we made? What happens when you share electrons between two atoms? You have a bond. Okay. Admittedly, this was typed, and that's kind of a bit obnoxious. Sometimes they show the bonds, sometimes they don't. You've made a bond to the hydrogen. Lovely. Okay. What happened to the bond between the hydrogen and the sulfur? It's no longer there because we took those 2 electrons and where did we put them? Look at our arrows. We put them onto the sulfur, which is why the sulfur now has 3 lone pairs, not 2. And because it has 3 lone pairs, we've learned how to calculate formal charge back in Unit 1, that when we look at sulfur, has 6 valence electrons, minus 6 non-bonding electrons, minus the 1 in the bond, gets us down to a -1, or minus the 2 in the bond, gets us down to a -1. And we now have the formal charge for the sulfur. That was all the Lewis structure stuff that we learned early on. We're now having to use all of that content. It doesn't just disappear, it gets used again and again and again. Okay? If we take a step back, okay, what's wrong with that first drawing? What would that result in?
Charge to the hydrogen from the oxygen is shown.
So that arrow shows sharing of electrons between the oxygen and the hydrogen, which means what?
Wouldn't it just all be connected then?
We have a bond between the oxygen and the hydrogen. Did we show anything happen to the bond between the hydrogen and the sulfur? Nope, which means
It's all connected.
it's still there. And that's what you would get. And why should that be a problem?
Well, hydrogen's exceeding.
Hydrogen can only have 2 electrons around it. We've exceeded its quote-unquote octet. That goes back to Lewis structure. So that's why that one doesn't make sense. We've exceeded the octet for hydrogen. That's not good. We did show the arrow is nice. We're going from the negative to the most positive thing, but we didn't acknowledge that we also have to break a bond. What happens in 2? What are they trying to show?
They're trying to show the hydrogen bonding to oxygen again, but they're not able to, because the atom doesn't move.
Therein lies the issue. Okay, what they're trying to do with that arrow is show the motion of atoms. Arrows don't show the motion of atoms. Okay? And that becomes probably one of the hardest things to deal with within organic chemistry, is that we do not show the motion of atoms. Okay? The only thing we can show is the making and breaking of bonds, which is ultimately the motion of electrons, and that's extra obnoxious because do we get to see electrons? No. If we think through all the things that we have the potential to be able to see, electrons are not among them. Okay? So we are moving invisible objects with our arrows. And we have to be very careful to understand that that's what's going on within those systems. What's happening in the next case? Okay. This first arrow, depending on how you want to count it, but that red arrow now is trying to move an atom. We can't move atoms. It doesn't happen. We move electrons. What's the next arrow showing?
Essentially creating a double bond between hydrogen and sulfur.
Yeah. We're taking the electrons from the sulfur atom and we're placing them into the space between the hydrogen and the sulfur, which means the net result is a double bond. You've put more electrons between the atoms. So that's extra problematic. Get it? Should we do another one or should we move on to a different question?
Do one more.
Okay. Is that because the last one's super hard? Where is it? There it is. Or there's one.
So same thing, it's showing the atom, the hydrogen moving.
We're moving the atom over, every curved arrow is referencing the movement of electrons. So if we're going to show that arrow, what we're saying is that hydrogen is taking the electrons. What electrons does hydrogen have access to?
The ones it shares with sulfur.
The ones in that bond. The arrowhead has 2 arrowheads on it. So if we look at an arrow, right, there's 2 heads. You could have a half-headed arrow also. 2 heads means
2 electrons.
2 electrons. How many electrons are in the bond?
2.
2. So if I show that red arrow, I'm taking the 2 electrons in that bond and I'm moving them this way. What's the blue arrow say?
That it's taking those 2 same
It's taking
electrons
2 electrons and we're moving them towards the sulfur. So we've got 2 electrons going 2 different directions. Doesn't fly. Kind of get it? Oh, 'cause I'm selling this. Okay. So rank. What's the strongest acid? What's the weakest acid? If you did some nomenclature, you might have a pretty solid guess for 1 right away. Anybody know what 4 is? Okay. That's an interesting line. We'll come back to that in a second. What did you suggest? That's wrong, and that's okay. So, and if we're not good with nomenclature, I don't blame you because I don't push it a lot because I hate nomenclature. I think it's obnoxious. I don't think it's worth the trouble. Okay, but the functional group in question 4 is a carboxylic acid, which would suggest
It's very acidic.
it's probably acidic. That's why we call it an acid. Okay, so that might be at the top. Okay. Before we get too jumpy, we need to evaluate everything else. Okay? There was one suggestion here, pKa. Okay? pKa is a measure of acidity. The smaller the pKa, the more acidic it is. So if you've memorized pKa's, you're in a hot spot because now you can be like, boom, here's all the pKa's. Now I know my ranking. The problem with that is what if you screw it up? You just screwed up the whole system. Okay? And instead, if we push based off of understanding what these molecules have to do, we don't have to memorize anything. We just have to apply the exact same logic again and again and again and again and again and again. And it gets obnoxiously tedious, but that's the point. It's supposed to be obnoxiously tedious that gets us there as quickly as possible. Okay? And why do I mention that? I was told that the pKa for structure 4 was 15. No, it's 4. Okay? And so if you've got it memorized wrong, you're dead in the water. But if you've spent time practicing how these things move and what these things mean, you increase the odds of being successful beyond a memorization. If you haven't been practicing, you're right. You are stuck in a boat. You better start memorizing like crazy and hope for the best. Okay? That's where memorization usually burns people with OChem. So you go, oh, I can just memorize things like I did in every other class. No, generally you can't. Okay? Because when you're asked to memorize something in another class, the way it's asked is the exact same. What's the number after 3? It's 4. Okay? I've memorized that. So when it shows up on a test, what's the question that's asked? What's the number after 3? Oh, it's 4. Like, that was easy. That was dumb. Okay? Except what we can go through and do is we can change this structure. What's its pKa now? That 15 is bugging me. Or how about now?
That's 16? No.
It's 4. It's pretty much the same. Had no effect on the overall structure.
Is the
But as soon as you change the structure, it looks like it changes. This is why memorization of facts in OChem is very, very dangerous. And I highly don't recommend it. Okay? So how should we go through and do this? Well, what must an acid do?
Donate hydrogen.
Okay? So what happens if that first molecule donates a hydrogen? What would it look like?
Negative oxygen.
Negative oxygen. Why not a negative carbon?
Because the carbon's not losing the hydrogen.
Why not?
Because they don't compete in terms of electronegativity.
There's a decent explanation. Okay? There are bonded. There's hydrogens bonded to each of those carbons. They're implied hydrogens.
I guess the
Okay? Why would I remove the hydrogen from there? Because if we look at the difference between the carbon and the hydrogen electronegativity, they're effectively the same, whereas the oxygen and the hydrogen are different. The oxygen's pulling on those electrons. You mean we can use fundamental principles to explain these? Yeah, that's the point of studying fundamental principles. I don't have to memorize those facts. What happens in the next one?
Nitrogen is going to steal the electrons from one of those hydrogens.
Why the nitrogen and not any of the carbons?
Because same thing, carbon won't steal from hydrogen.
Why not?
Their electronegativity is equal.
If you go back to the fundamental principles, their electronegativities are the same for carbon and hydrogen. There's no reason for it to steal the electrons. There are cases where carbon can steal those electrons. That's looking to deeper effects. Okay? And we will see those later in the semester. Okay? Why else should we jump on the nitrogen hydrogen?
Because the nitrogen is electronegative.
Nitrogen's electronegative and
Oh, it's positive.
it's positively charged. Knowing nitrogen's electronegative, does it want to be positively charged?
No.
No, so what's it going to do? Steal electrons. What's the easiest thing to steal electrons from? Hydrogen. So there we go, we get that structure. How about structure 3?
That's not an acid, right?
To act as an acid, what must it do?
It has to have a hydrogen proton.
Does it have a proton to donate? No. So can that be an acid? No, which means?
It's number 4.
It's number 4. It's the bottom. It's the not an acid. What happens with the last one?
Oxygen steals the electrons from the hydrogen, becomes negative.
And why did we not steal them from the carbons?
Carbon will steal from hydrogen in this
Why won't carbon steal from hydrogen?
electronegativity.
The difference in electronegativity is so close. Okay? So this is why knowing those electronegativity trends that we talked about back in Unit 1 come back and bite us. Okay? We have to think through those approaches. Okay? So now what do we have to do? Rank? What am I using to rank? So we'll say not acidic. And we'll say acidic. So we do have one option, right? 3's got to be at the not acidic. Okay? And if you're stuck in a multiple choice environment, get that and hope for the best and hope you can eliminate at least an answer.
Would number of hydrogens on electronegative atoms make any difference?
The number of hydrogens ultimately has no effect because you can only remove one at a time. So all we care about is the removal of one. You could go through and then say, well, it has another one. Could it do another one? Yeah, it could.
In a second step.
Okay, in a second step. Okay, but that's a subsequent step. You're more concerned about the first one, particularly in a system like this where you're being asked to rank acidity. Okay, so it would be nice if we had a ranking system that would help us evaluate how to go through these. And the very first thing that on that ranking system is, charge. So we could go through and look at our 3 remaining structures and see if there's charge. So is the first structure charged?
Yep.
How about the second?
Nope.
How about the third? Yep, so there's a difference. Okay? When a reaction occurs, do we want to make charge or get rid of charge?
Get rid of charge.
Okay? So if I want to get rid of charge, does that help me to differentiate now?
Would it be
I don't even need to worry about size yet. I've got charge to deal with because I have a difference right out of the gate with the very first rule, charge. Which one of these reactions, red, blue, or black, produces the most stable product?
blue?
Blue, because
It's neutral.
it's not charged. We're using charge to evaluate that. And since it's the most stable product, what does that mean about the H plus that's also produced? It produces more of it. And if it produces more of it,
More acidic?
that makes 2 the most acidic. How do we differentiate between red and black then? What else should we evaluate beyond charge?
Size.
Size. Cool. What do you know about size? Is there a difference in size? And this
Yes.
becomes the hard part. Some very confident yeses in size. What is the atom holding the charge in 1?
Are we just looking?
It's oxygen. What is the atom holding the charge in 4? Oxygen. Do they have different sizes?
No, but there's 2 oxygens.
That's true, there are 2 oxygens, but when we're looking at stability, we don't look at the extraneous things, we look at the primary focus. 2 people are running at you down the road, okay? One looks like a big shadow, the one looks like a small shadow. Who are you more concerned about?
Big shadow.
The small shadow's carrying a samurai sword. Your focus has probably changed, right? Okay. So we start at the extremes and then we slowly work our way down. Okay. So charge, size, electronegativity are all atom effects. They're directly relevant to where the charge is. After that, if you can't tell a difference, so like in this case, oxygen versus oxygen, what do you now need to do?
Resonance?
Now you need to expand beyond the atom and look at how the molecule can now affect it. Okay, well, how could the molecule affect it? Resonance. What does resonance do?
Moves electrons.
Moves electrons around. And if electrons can move around, does that stabilize or destabilize them?
It depends.
I mean, it does sort of depend, but generally speaking,
Stabilize.
it stabilizes. The more you allow your electrons to disperse, the less reactive they become. Okay? So if we now look back to these 2 molecules, do we see an option for resonance? For structure 4, we have the ability to donate the electrons in and shuttle those electrons up. Okay? One of the confusions that students will sometimes pick up will be like, but the charge didn't change. I don't care that the charge didn't change. I care what happened to the charge on an individual atom. This atom is constant. What happened to its charge?
It's now neutral
Did the charge change?
on that atom.
On that atom, it did. That's a stabilizing effect. Okay? You're now distributing the pain, if you will, across multiple people, not across one atom. Whereas in the other case, that charge is distributed only on one atom. So what does that mean for us?
4 is more stable, therefore more acidic.
4 becomes the more stable product, and because the product is more stable, it produces more H plus than does 1, which gets a little bit less H plus. This one gets a whole lot, more H plus, and that green one had no H plus. Kind of, sort of. So what you end up doing is slowly, methodically moving through those rule sets. Those rule sets allow you to predict a lot of chemistry. Okay? And if you don't want to predict, that can be okay too. That just means you need to memorize. If we look at the number of reactions that we'll study this semester, you're probably on the order of 40 reactions. Okay? Realize that when I say 40 reactions, this molecule, the one I'm circling now, our carboxylic acid over there, okay, that molecule is the same reaction as this molecule, as that molecule, as that molecule, as that molecule. And yet the structure changes so much that what does it look like? An infinite amount of other reactions, and everybody will get lost in the noise of the structure as opposed to the reactivity of the functional group. This is why it's important to zero in on recognizing functional groups, because that's where their primary chemistry falls. Kind of, sort of? Questions? Okay. Should we keep rolling through this one? What is wrong with the following mechanism step and give an alternate way in which the two species could react? Draw the product that would form.
The oxygen wouldn't donate its electrons to that carbon.
Why not?
Because oxygen is electronegative and it steals carbons. It doesn't want to donate them. And carbon wouldn't steal them from oxygen.
Once locked into a bond, sure. But can we run a reaction where oxygen shares electrons with carbon? Absolutely. So unfortunately your explanation is flawed, and then we lose a lone pair. What is the problem with all of that?
Carbon succeeded.
How many bonds can carbon have?
Isn't
Do-
there an applied hydrogen on the...
It's going to be like, don't let my question chase you away.
Because now it technically would have 5.
1, 2, 3, 4. But what she's saying is there's also a hydrogen. How do you know there's also a hydrogen there?
Implied.
It was implied at the very beginning because that carbon was neutral. There had to have been an implied hydrogen there to satisfy the octet of the carbon, which means that same implied hydrogen's there at the end because we showed no curved arrows to show anything happening to said hydrogen, which means the resulting structure has exceeded the octet and we're not allowed to do that. Okay? So is there an alternate way in which we could react these two species? You get a couple different options that you can pull off out of this. Officially, there's actually something wrong with the structure to begin with. So let's try that. Take a look at that starting drawing. What's wrong with it?
Is nitrogen
Good.
missing a charge?
I would argue it's less nitrogen missing the charge and more that it should not have that lone pair, and then should also have the positive charge. So as it's drawn, it's exceeded the octet. It has more than 8 electrons around it, and that's problematic. So that nitrogen should be positively charged, or we delete a hydrogen. So there's a whole variety of ways that we could modify that structure to make sure that it matches that. How did you see that issue?
Because it's not right.
Okay.
Well, I mean,
So-
you can count all the electrons other examples, I'm saying just from,
When nitrogen has had a lone pair, it has actually not had a charge.
or we've added a charge in moving something around.
So typically when a nitrogen has a lone pair, it's neutral. There have been I can't think of any cases where we would have had a negative nitrogen. But if we had a negative nitrogen, it would have been 2 lone pairs. So I guess perhaps a different question. Does everybody see what she's saying? The way you just stared at that makes me think that's a no. You don't see what she's saying.
I don't remember exactly what she was saying, so I'm more so trying to remember what she said.
Nitrogen's, well, okay, so I'm saying from the, why I'm like, that's wrong, that doesn't look right, is
Which is a good
because
reflex.
even in 4, in 3, or 2, like all of the nitrogens there are all positive, they all have a charge.
Where are we? 2, you said? Yeah.
4 and 2. So then you just look at that and you go, it has a lone pair and it's double bonded, but there's only 2 hydrogens there. Something's wrong. Just like initial, and then you can count out all of its electrons around it and see that it's.
So let me walk through that and see if I'm seeing it the same way you're describing it. Is that you looked at the nitrogen and saw that you had 4 bonds. And when you see 4 bonds, you don't see lone pairs when you've seen it before.
Just like instinctual, like without thinking about
That's
it,
fine.
just looking at that and saying, that doesn't look right.
Yeah.
So something's wrong. What's wrong? Count everything around it and then, okay, either
Yes.
get rid of something or move something.
Okay. And instinctual is not a problem per se. The issue that I have with instinctual is the only reason it's instinctual for you is because you've had that experience. So you've done practice. If you haven't done practice, do you have that instinct?
No.
No. Okay. Which could be the bucket that the rest of the class is in. So if you feel like you haven't been doing a lot of practice, you're in a situation where you can't do what she's suggesting. Okay. I would push it even further. It needs to go beyond instinctual, and you should look a little bit more carefully at it. One of the things that can help is instead of looking at simplified drawings, look at the complete drawing where you see all the bonds. How many electrons are now shown around that nitrogen? Damn, that was fast. Have you already been counting it, or did it just...
I just said 2, 4, 6, 8, 10.
Nice. Okay. 10. How many electrons are supposed to be around it? 8. There's a problem. We can't exceed the octet. How do we know that? Because we did that in Unit 1. That was the whole point of looking at Lewis structure, was to recognize we can't exceed octets. Why? So that when we encounter things like this, we can be like, dude, there's a typo here. This is a problem that shouldn't be there. Okay. So let's fix it. Let's get rid of that lone pair. So this is one way we could have fixed it. Okay. We're still going to encounter the same problem at the end, okay, because there's still an implied hydrogen here. We would have exceeded the octet on that oxygen. So what could we add to this to fix it? So again, said another way, this carbon is going to be very problematic because it will have exceeded its octet with this single arrow.
So could you donate a hydrogen to take away?
Okay. Donate a hydrogen. So donate a hydrogen means I have a base come in and I come in and pick up that hydrogen. Okay. So donate hydrogen very specifically is referring to H+, which means what happens to those electrons? They stay on the carbon. Does that fix the problem? No. So what you could go through and do is say, have hydride be lost. So now you're saying H minus. So that satisfies that. Okay, I can get behind that. Would we say that's a good move? I was pretty confident no. Why is that a bad move? Just because of how I said
I
it?
just think it looks kind of messy right now. It doesn't look pleasant right now.
Which looks messy?
Um,
The H minus or all the curved arrows?
Both, yeah, but H minus and the curve.
H minus looks messy? That's an
Well,
H with just 2 dots. How
I
is that
guess
messy?
More so to like interpret it, I guess. I just don't like how it looks. I don't like
That's
it.
a good reflex. That's a good reflex. And this becomes one of the things that we have to build on. You have to go beyond reflex. Test day, absolutely. Grind the hell out of your reflex. Class period isn't for reflex. This class period is for figuring out why your reflex is good or bad. How do we stabilize a negative charge?
You add positive.
Okay, you could add a positive, but how do you stabilize a negative charge on its own? That's not on its own. What do you look for after charge to evaluate stability? But we could look at electronegativity. Is hydrogen particularly electronegative? No, in fact, it's one of the lowest in the electronegativities, which means can it stabilize that negative? No. So while this is a decent idea to fix octets, this is going to be a problem because hydrogen can't stabilize that negative charge very well based off of its electronegativity. What should you look at before electronegativity? Size. Is it very big? No, this is hydrogen is the smallest atom. You're taking a pair of electrons and placing it in the tiniest possible space possible. Is that a good thing or a bad thing? That's a bad thing. That's a really bad thing. Okay? When we talk about stability of charges, we want that charge spread out over a large area. Okay? So H minus is incredibly unstable. Does that satisfy the arrow pushing? Yes. Okay, I accept that. It does. Okay, is there something else you could have done that would have been better? As I show the letters underneath. You got to the right idea. We needed to get electrons away from that purple carbon.
The other H was connected below, move back since.
Connected below, we're talking about the purple carbon that only has one H connected to it. What bonds are connected to that purple carbon? So single and double, cool, do better. Because we've defined single and double differently. Sigma and pi, which one's a stronger bond, sigma or pi? No. Sigma's the stronger bond because sigma is the direct overlap of orbitals. The pi bond had no direct overlap of orbitals. The pi bond is weaker. What you are trying to say is that a double bond is stronger than a single bond. Yes, it is. That's because it's made up of two bonds, a sigma and a pi. That's why a double bond is stronger than a single bond that only is made up of a sigma bond. The pi bond is by far weaker. So if we're going to have that oxygen come in there and exceed the octet of the electrons around that carbon, the bond we want to break is the pi bond. And we want to move those electrons away towards the nitrogen. This is going to solve two problems. We fix the octet, and what happens to the nitrogen? Yeah, it was positive, except it just gained electrons, which means it's now neutral. You've stabilized it. What you're trying to do is take advantage of ways that you have charge imbalances and how you can move those electrons around to satisfy and either stabilize or destabilize varying structures. Okay? For the sake of this class, what we're going to do is stabilize. You do not want to destabilize anything. So what happens is a potential product out of this, and then that's where we'll end. The oxygen, having shared its electrons, will now become positively charged, and you've now shifted where the positive charge appears. The chemistry happening in this particular reaction is a challenging chemistry. Okay? It is one that shows up in second semester organic chemistry, so I find it infuriating that we try and cram all of this content into one semester. But somebody other than me thought it was a brilliant idea to do this and inflict this pain upon y'all as students. I just happen to be the one that's been tasked with that job. Okay? Why this reaction works falls on a bunch of other chemistry that you were never taught, because it's not taught in Chem 130. It's taught in general chemistry. So what are you expected to do? You're expected to memorize that certain reactions just work. And that is a problem, in my opinion. With that, we are beyond our class time, and we need to get a little bit of a break in before we start lab. Hooray!